the product rule. We're going to be interested in having a rule when we have the derivative of a product. So if we had two functions, f and g, if we took the derivative of f, we could use the power rule, power out in front, and then decrease the power by 1. If we took the derivative of g, we could use the power rule, power out in front, decrease the power by 1. Now, if we multiplied these two derivatives together, we would get 12x to the fifth. However, if we took the two functions, f multiplied by g, we'd keep the base and add the exponents. And then if we took the derivative of these two functions, we would have power out in front, decrease the power by 1, and you can see this does not equal that. So the derivative of a product is not the product of the two derivatives. All right, well, let's look at a geometric derivation to see what the derivative of a product should be. So we're going to let u equal f of x and v equal g of x, and these are going to be positive differentiable functions. So the product uv geometrically would be, we could look at that as the area of this rectangle. Now if we wanted to add a little piece, we're going to call that delta u. This is our f of x plus h minus f of x, and we could add a little piece for our g of x as well, and we're going to call that one delta v. So geometrically we would have u plus a little change in u along here for our length of our rectangle, and we would have v plus a little delta v for our width of our rectangle. So looking at this in terms of areas, we could see that the area of this whole thing would be u plus delta u multiplied by v plus delta v. Now we could take this and we could express our little change in uv then, and our change in uv would be this whole product, or this whole rectangle here, minus this original white piece. And so here is the big rectangle minus the area of uv, and you can see that that would leave us these three pieces, and we could find that by looking at this geometrically and expressing the area of these three shaded rectangles. Or we could also take this and compute this product and see, because if we multiplied first times first, we would have uv and it would cancel with this minus uv. When we did outers, we'd have u times delta v, and that is in fact the area of this rectangle. When we do inners, we would have delta u times v, or v times delta u, and that would be the area of this blue rectangle. And when we did last times last, we would have delta u delta v, the area of this rectangle right here. So we can express our change in this area then as this sum of these three rectangles. So we're going to take this little change in the product, and we have it expressed here as those three rectangles, and we're going to divide everything by delta x. And then we are going to take the limit as delta x approaches 0, and the reason we'd want to do this is essentially this is just the Leibniz definition then of the derivative. So we could express the derivative with respect to x of these product of these two functions u and v as the limit as delta x approaches 0 of the delta uv over delta x. Now that would then equal the limit of this right hand side, and then we know with properties of limits that the limit of a sum is the sum of the limits, and so we could compute the limit of each piece. Now the other property that we can utilize is this u and this v do not depend on delta x, and so we can move them out in front and multiply them in front of the limit. And we also here have two things that do depend on delta x, and it's the limit of a product, and so we'd express that as the product of the limits. Now let's just look at these and see what we have left. This is just the Leibniz notation of the derivative dv dx, and here we see Leibniz notation derivative du dx. Then looking right here, because we know how we define delta u, if delta x approaches 0, then so does delta u. So this is going to go to 0, so we would have 0 multiplied by this one is just, looking at that Leibniz definition, this is just dv dx. So as we express these in terms of the derivatives, this is what we have left, and of course 0 times this one will be gone. And so we now see our product rule. The derivative of the product uv is u dv dx plus v du dx. When I use the product rule, when I see a product and I need a derivative, I just say this as I do it. I say first times the derivative of the second plus the second times the derivative of the first. So of course u is our first function, v is our second function. So first times the derivative of the second plus the second times the derivative of the first. And if you'll say that as you do that, you will get the product rule memorized. Here we have two functions of product. Our first function is v squared and our second function is 2 square root of v plus 1. So to compute this derivative, we have the first function multiplied by the derivative of the second function, and computing the derivative of the second function, this is 2v to the 1/2 plus 1, and we know the derivative of the sum, we can differentiate each term. The derivative of this term would be a power rule, so we would move the power out in front and decrease the power by 1, and then plus the derivative of a constant, which is 0. So in simplifying this, this would leave us with v to the negative 1/2, and we'll go ahead and multiply those in a minute. So this was first times the derivative of the second. So this v to the negative 1/2 is what we get when we differentiate this second function. Plus the second, now the second function has two terms, so we'll need to put that in parentheses, multiplied by the derivative of the first function, and that's just going to be a power out in front, decrease the power by 1. So this will be multiplied by 2v. So our final answer here, we could go ahead and multiply these together, and we keep the base and add the exponents. So 2 minus 1/2 would be v to the 3/2, plus multiplying or distributing this one through, we have 4v to the, this is 1, which is 2/2, of course, 2/2 plus another 1/2. So this would be a v to the 3/2, and then plus 2v. Now we have some like terms we could combine, so we have 5v to the 3/2 plus 2v for our derivative of this product. Let's go ahead and look at one more example. We have the product of x squared and e to the x. So our product rule says the first function multiplied by the derivative of the second function. The second function is e to the x, and we know the derivative of e to the x is just e to the x, plus the second function, and that's e to the x, multiplied by the derivative of the first function, and that's just a power rule, so multiplied by 2x. So this is the derivative of x squared e to the x. This is sometimes written factoring out the common e to the x. So we could also express this derivative as, actually, once I get that, I could see that there's also an x in common. So we could factor the common factors out, and we could also express this like this.